So welcome back to my lectures on Galois theory. So we are going to start the main topic of the entire course, and that is Galois theory. So what I want to do initially to start with is to list all the important results what we have done so far, because we are going to use most of the theorems, most of the important theorems that we established. So let us start with listing the very important results that we'll be using it for this theory. So before that, for all these results, I'm assuming that E is if an extension of F, of a field F, and that is F is less than or equal to E. So that I don't need to write these statements in every results. The first one is if alpha comma beta belongs to E are algebraic over F, then there exists an isomorphism psi of alpha comma beta from f of alpha to f of beta that leaves F fixed and maps alpha to beta. That is, alpha of alpha beta of alpha is equal to beta. This is a very important theorem in the whole Galois theory. So second one is that any automorphism on F closure that leaves F fixed maps every element in E to its conjugates. Next one is the collection of all automorphisms living or on E, leaving F fixed. E is a group, normally we'll write it as G of E over F under function composition. Then the set of all elements in E that is fixed by all elements of a subset S of G over F forms a subfield of E denoted by ES. It's called a fixed field of S. And F is always a subfield of E of G of E over F. The fixed field of the group. So the fourth one is, if E is a splitting field, then every isomorphism on E leaving F fixed is an automorphism. Then, and the order of the Galois group of E over F is equal to the index of E over F. This is a group of automorphisms, and this is a number of isomorphisms from E to F closure. When it's a splitting field, these two are same. Now, let us do the next one. If E is a separable extension, then the index number of isomorphisms from E to F closure is equal to the degree of E over F. And for every alpha in E, the irreducible polynomial of alpha over F has all zeros with the multiplicity 1. Our basic aim is to bring the order of the group of E over F is equal to the degree. So, if you combine these two, it has to be a splitting field. Well, in this case, I'm assuming that E is finite. Here also, E is a finite extension. So, if you combine these two, E is a splitting field here, is a separable extension, and both are finite. Then you can have the order of the group of automorphism is equal to the degree. So if E is a finite separable splitting field, then the order of Galois group of G over F is equal to the degree of, and this leads to a new definition, and that's where we are going to start the Galois theory. So if E is a finite splitting field over F, then the order of the Galois group is equal to the index of E over F. This is the number of isomorphisms on E leaving F fixed. This is the group of automorphisms on E leaving F fixed. If it's a splitting field, then the isomorphism becomes the automorphism. That is our fourth result. And that is why these are equal. If E is a finite separable extension over F, then its definition itself is index is equal to the degree. But you remember the necessary and sufficient condition for an extension to be separable is that the irreducible polynomial of every element has zeros with multiplicity 1. So we are going to combine these two to form a new definition. A finite extension K of F is called finite normal extension if it is a separable splitting field. Separable splitting field. For example, Q of root 2 is a separable splitting field over Q, and therefore Q of root 2 is a finite normal extension of Q. And in fact, the degree of Q of cube root of 2 over Q is equal to 2, and that is equal to the index of your F. So before we come to the main theorem, we need to establish one more result. So that is, let K be a finite normal extension of f and E be an extension of f such that E is an extension of f which is a subfield of K. That is here. This is our f, this is K, and there is a extension here in between, and that is E. This is a finite normal extension, meaning this is a finite separable splitting field. Then K is a finite separable, K is a finite normal extension. Finite normal extension of E. K, this is given, but if you add one more field in between, then this will be a finite normal extension of E also. Just like we did the separable extensions. So this is the first part, and the group of automorphisms on K leaving F fixed, leaving E fixed, is a subgroup of automorphism on K leaving F fixed, meaning this is also K and this is a subfield F, this is another subfield E. So there are a lot of automorphism going on from here to here. Some of them leaves F fixed, some of the leaves the whole E fixed. So what this says is the group of automorphism on K leaving E fixed is a subgroup of K automorphism on K leaving F fixed. Now the third part is when you map automorphisms from K to K, see this is a subgroup, meaning there are some automorphisms on G of K over F that is not an automorphism here. So let us say gamma is an automorphism on K to K leaving F fixed, meaning sigma of A is equal to A for all A in F. That does not mean that if you take an element from here, it should match the same element. Meaning that doesn't need to be an automorphism on E. That is why it's a subgroup. But still it will be an isomorphism. So sigma from K to K becomes an isomorphism when we map an element from E. That means sigma restricted to sigma restricted to E does not need to be an automorphism. But still it is an isomorphism. Meaning if you take an element here, it may be an element here but it's a different element, or it may be an element even outside. So sigma can match here, or sigma can go here also. Or it can go here also, and that is the case when it falls into G of K over E. So, but so if you take two of such automorphisms on K, which is not in here, both of them actually induces isomorphism on E. So the next statement is to compare those isomorphisms. So sigma and tau induces same isomorphisms on E. Sometimes it will be an automorphism, and that's the time when both of them will be in here. But still it will induce isomorphism. So induce the same isomorphism if and only if sigma and tau belong to the same coset, same, to be precise, left coset of G of K over E in G of K over F. When you say coset, if H is a subgroup of G, then the coset of A plus H is defined as A plus H, H belongs to H, for some A in G. So if this actually, these two are actually now, this is actually G of K over E, which is a subgroup of G over K over F. What are the elements here? Elements are automorphisms. So if tau, sigma and tau belongs to G of K over F, they actually induces same isomorphism if sigma plus G of K over E is equal to tau plus G of K over E. That is what the next statement is, and we'll do a detailed proof. I just want to explain the theorem first before we come to proof. So there are three parts to this proof. The first part is if F is a subfield of E, which is a subfield of K, and K is a finite normal extension, then we need to show that K is a finite normal extension of E. What is given? K is a finite normal extension of F. We need to prove that K is a normal extension of E. Second one is G over K over E is a subgroup of G over K over F. Third one is sigma tau belongs to G of K over F induces same isomorphism on E if and only if sigma plus G of K over E is equal to tau of tau plus tau plus G over K over E. Left cosets. So these are the three points which need to prove. So first one, K is a finite normal extension of F. And that implies K is a separable extension of F. And that implies K is a separable extension of E. All are finite, so I'm not even considering finite. Another thing which we need to prove is, see, in order to prove that K is a finite normal extension of E, we need to prove that K is a finite separable splitting field of E. So we need to still prove that K is a splitting field of E. So K is a finite normal extension of F implies K is a finite splitting field of F. And that implies there exists a collection of polynomials in f of x for some index set I such that all zeros of all elements, let us say S is equal to elements of S are in K, and that implies see these polynomials are in f of x. These polynomials are in f of x mean these polynomials are in E of x, because all the coefficients of f means all the coefficients are in E, because E is an extension of f. So this implies there exists, or this implies S is equal to f of I of x belongs to E of x, such that I belongs to I, such that all zeros of all elements of S in K, and that implies K is a splitting field over E. So that means K is a finite separable splitting field of E, and that means K is a finite normal extension of. That is the first part. The second part is we need to prove that the group of automorphism on K leaving E fixed is a subgroup of the group of automorphism on K leaving F fixed. So let sigma belongs to G of K over E. That implies sigma is an automorphism on K leaving E fixed. When it leaves E fixed, definitely it is going to leave F fixed, and that implies sigma is an automorphism on K leaving F fixed. That only means this is a subset of this group. How do you prove it is subgroup? It's already a group. So since G of K over E is already a group, it is a subgroup of G of K over F. In the third part, we have another two subsections. So let us start with the two elements from G of K over F. So let sigma tau belongs to G of K over F. Sigma comma tau belongs to same left coset of G of K over E in G of K over F if tau inverse of sigma belongs to G of K over E. See, if H is a subgroup of G, two elements like A1 comma A2 belongs to A plus H, then A2 inverse of A1 should belong to H. So that is the result I'm using it here. It's coming from group theory. So that implies there exists a mu in G of K over E, such that tau inverse of sigma is equal to mu. And that implies you compose tau on both sides, sigma is equal to tau mu. So let us take an element, let A belongs to E. That implies sigma of A is equal to tau mu of A. Where is mu from? Mu is from the group of automorphism living E fixed. And where is E from? A from? A is from E. So this is actually A, and that is equal to tau of E. What does this mean? For all A in E, sigma of A is equal to tau of A. That implies sigma and tau induces same isomorphism on E. That is one part. Now assume that sigma and tau induces same isomorphism on E. So what does this mean? For all A in E, sigma of A is equal to tau of A. And that implies sigma inverse of tau inverse of sigma of A is equal to A. What is this? This is an automorphism on E. That is actually not an automorphism, but identity map on E. That means tau inverse of sigma belongs to group of automorphism on K living E fixed. We are living E fixed for all A in E. This is living A fixed. So this belongs to here. And that implies tau and sigma are in the same left coset of G of K over E in G of K over